All right, young scientists, this will be our last screencast for Unit 8. We're going to talk about phase changes, which is actually something you've learned about at length. You did it in Chem 1, we did it again a little bit in Chem 2, and even here in AP. I just want to go over some things and talk about some applications you may not have put together before. So, you know about phase diagrams, you know about solids, liquids, and gases, you know about the transitions in between. Hopefully, you were in class to see the triple point of carbon dioxide. We also have the critical point up here where we have a supercritical fluid beyond that, which has properties of a gas and a liquid. Real fancy there. It's pretty cool, but not something that we really interact with here on Earth very much. This is all review stuff that you've seen before. You've also seen the heating curve, which is basically the graph that you would get if you measured time. Like if you heated up a solid for an extended period of time, you would see its temperature increased until it melted. Then the liquid's temperature would increase until it started to boil. And if you contained that gas, once it was all done boiling, that gas would start to heat as well. This is what we call the heating curve. And you used it to talk about MC delta T, M delta H, MC delta T, M delta H. Now, a few applications, though, are things like vapor pressure. We talked about vapor pressure with gas laws and how if you have like a container of water, some of the gas in that room will be water that's come from the liquid. If you think about just leaving out a glass of water on a tabletop, that water will eventually evaporate, even though it was never actually at its boiling point. Some of the molecules were moving fast enough and in the right direction to fly out of the liquid and as a gas then. The stronger the intermolecular forces, though, the harder that is to happen, which means that your vapor pressure will be decreased. So vapor pressure is liquids spontaneously becoming gases. This will naturally occur with any liquid, but it occurs less the stronger the intermolecular forces are. You also saw with the gas laws that if the temperature is increased, that means the average kinetic energy of the liquid is increased, and it's more likely that those particles will be able to escape as a gas. So vapor pressure of water is temperature dependent, and you looked that up in tables. If you add a solute to your liquid, the intermolecular forces between the solute and the solvent are going to make it harder for that solvent to escape as a gas. So there's attraction between my blue liquid particles and my pink aqueous particles, and that makes it harder for those liquid particles to escape as a gas. This is going to depend on the number of solid particles, so if you have a higher concentration, it's going to decrease the vapor pressure as well. Now, one of the things we see with this, it's really the same phenomenon, is what we call boiling point elevation. So when you dissolve something in a liquid, it increases the temperature that's required to boil that liquid because you have attractive forces between the particles in solution and the liquid itself. So whoever told you that you need to salt your pasta water in order to make it boil faster was lying. That's not how it works. It'll actually boil at a higher temperature because you've added that salt. The salt is there to season the pasta. We see really the exact same principle on the other end of the spectrum with freezing point. If you have particles in your solution, it makes it harder to form the solid crystalline structure that occurs when a liquid becomes a solid. So adding a solute to a solution drops the freezing point. It has to be colder in order to freeze. This is why we salt the roads. Adding salt drops the freezing point of liquid water. So if it's 20 degrees outside, but we salt the roads, the freezing point of the water drops from 32 Fahrenheit to something below 20, and now the ice is no longer a solid, it's a liquid. This is also why if it gets sufficiently cold outside, salting the roads doesn't help anymore. If it's still below that new freezing point, it'll still freeze. So a couple years ago when we had those multiple days of minus 40 degrees in a row, it didn't matter how much we salted the roads were still frozen over. So these are mostly things that you've already seen before. I just want to talk about vapor pressure a little bit more, and boiling point elevation and freezing point depression. Remember, boiling point elevation and freezing point depression are really the same principle on either end of the spectrum. When you have other stuff in with the liquid, it makes it harder for the phase to change. All right, that's going to wrap up Unit 8 here. If you have any questions, please let me know. Thanks for listening along.